All right, so let's calculate the net force that your hand exerts on a 6.5 Newton upward force on a half kilogram of sugar. Considering the force of gravity, that's a downward force, what's the net force that's acting on the sugar? And we can give the magnitude and the direction. So first of all, our free body diagram, we know that there's a normal force upward. That's the 6.5 Newton force that's being applied by your hand. And then the force of gravity downward, which is 0.5 times 9.8. And that gives us 4.9 newtons for our force of gravity. So when you actually take that 6.5 newtons upward minus the 4.9 newtons downward, you get your net force, which is going to be 1.6 newtons of upward force. So the normal force, as we mentioned before, the normal force is the force that acts between any two objects that are in contact with each other. And it's always perpendicular to the surface, which is actually where the term normal comes from. The term normal is a mathematical term that means perpendicular. So with two surfaces that are in contact with each other, like this box and this table, the normal force is always going to be perpendicular to that surface. So let's do one example where we have to find the normal force. Now, let's suppose we have a 10 kilogram box that's sitting on the counter and it's not accelerating. What's the normal force? Well, we can use Newton's second law where net force is going to be equal to mass times acceleration. Since there's no acceleration when it's not accelerating, the net force is going to be equal to 0. Well, the only forces acting on it are the normal force upward and the force of gravity downward. So that means the normal force upward is positive, the force of gravity downward is negative. We have our equation to find the force of gravity. That's mass times gravity, which is 10 times 9.8. We go ahead and calculate that, take that to the other side. We figure out that the normal force equals 98 newtons. So the weight of the object is 98 newtons. So the normal force has to be 98 newtons in order to balance it so that it's not accelerating. In this example, we have a force that's being pushed downward with 50 newtons. Well, we go by the same scenario. It's still not accelerating, so the net force is going to be equal to 0 newtons. Now we have an upward force, a normal force, but we have a downward force of F1, which is this 50 newtons. Now that's downward, so it's going to have a negative. The force of gravity is downward, so it's going to be a negative. Normal force is upward, so it's going to be positive. And it all adds together to be equal to 0 because it's not accelerating, because the net force is going to be 0. Alright, so we plug in our numbers. 10 times 9.8 is going to give us 98, and then we have negative 50. That gives us a total of negative 148. We take that to the other side. The normal force is going to be equal to 148 newtons upward. Now that should make sense because that balances not just the weight of the object, which is 98 newtons, but it also balances this 50 newtons. So it has to be increase in order for it to be balanced in 148 newtons total. In this example, now we're pulling upward with 50 newtons, so now the 50 newtons is going to be positive. So net force is still going to be equal to 0 because we're still not accelerating. The upward force of normal force minus the downward force of gravity plus this other force, force 1, that's going to be upward as well. The net force is going to be equal to 0. Go ahead and plug in our numbers. 10 times 9.8 gives us 98 plus 50. Now that gives us negative 48 newtons. We take that to the other side, becomes positive 48 newtons. Now this should make sense also because now we have this 50 newtons helping to balance out gravity, so we don't need as much normal force. And normal force doesn't equal 98 because we got this 50 newtons that is also helping. So this is an example where the normal force is not equal to the weight because we have some other force that's helping out. So you got a friend Larry, he's sitting at the lunch table with his friends, and he wants to sound smart. So what he says, did you know that there are forces acting on you? Because Newton's third law, the normal force acting on you by your seat and gravity are equal and opposite. Now the reason that Larry is actually incorrect in saying this is because the forces that are equal and opposite in Newton's third law always act on the same two objects. So for example, you're talking about the normal force acting on you by your seat. Newton's third law says a force on the seat by you. That's what Newton's third law says. Gravity is the force of the earth on you. So Newton's third law says that you apply a force on the earth. That's Newton's third law. Now, when you're talking about the force, the normal force of the seat and gravity pulling down, those are equal and opposite, but that doesn't mean that it's Newton's third law. Newton's third law only applies between two objects. When you talk about the normal force of you and the seat, there's your two objects, and then gravity on you, gravity of the earth, that's a third object. Then you're talking about balance forces. When two forces are equal and opposite, they're balancing each other, which gives you a net force of 0. But if I took that seat out from under Larry, gravity would still be pulling on him. So that's not Newton's third law. All right. So here's a question. What does the bathroom scale read? When you step on a bathroom scale, what does it read? Well, there's two possibilities. it either reads the upward force of normal force or the downward force of gravity. Now think about how a bathroom scale works. Does it push up on you or does it push down on you? And the answer is that it pushes upward. Since it pushes up on you, then that means it has to have the upward force, which is going to be the normal force. And this fact is what we're going to be using in our next PowerPoint. In this PowerPoint, we talk about the force that a scale is applying to a person that is in an elevator. As a person rides an elevator up and down, he has certain accelerations that are being applied to him. The scale doesn't read the weight of an object, it actually reads the normal force that's being applied to an object. So as an object goes up and down in an elevator, the force of gravity is constant, but the scale force has to change in order to account for the acceleration up or down. So a couple things to keep straight before we move on. Displacement, velocity, acceleration, and net force. So which one of these always occur in the same direction? Can you have a displacement without a velocity? Can you have a velocity without a displacement? Absolutely not. If you have a velocity, you got to have a displacement. You're going somewhere, so you have to have a velocity and a displacement at the same time. What about acceleration and net force? Can you have an acceleration without a net force or a net force without an acceleration? Newton's second law says net force equals mass times acceleration. So if you have zero net force, you're going to have zero acceleration and vice versa. So the trick comes in, the question comes in with these two right here, velocity and acceleration. Can I have a velocity and not have an acceleration? Well, an object that is moving at a constant velocity is not changing its velocity. And the definition of acceleration is change in velocity over time. So if it's not changing its velocity, there's no acceleration. So an object moving at a constant speed has no acceleration. Now, is it possible to have an acceleration with no velocity? Well, if you think of an object that's moving upward and it stops at the very top before it starts coming back down, at that moment in time it has a zero velocity, but it still has an acceleration of negative 9.8. So we have displacement and velocity that have to have the same direction, and acceleration and net force have to have the same direction. The reason I'm pointing this out is because when we start talking about the forces that are being applied in an elevator, a lot of times we think of the velocity, the direction of motion, when we start thinking about net force, but in fact we have to think about the acceleration, the direction of the acceleration. That determines the direction of the net force. So the direction it's moving is going to help us to determine the direction of the acceleration, but the direction it's moving has no effect on the net force, just the acceleration. So we have this guy riding on an elevator, and he steps onto a scale, and the scale is going to tell us the normal force, the upward force that's being applied. His weight is the downward force. The downward force is not going to change. The weight of an object doesn't change when you're at the surface of the earth, but the upward force can change in order for a person to accelerate. In order for him to accelerate, you have to have unbalanced forces. Now, since the downward force doesn't change, that means the upward force has to change in order to allow for the forces to be balanced or unbalanced. Now, as he steps onto the scale at the beginning and he's not moving yet, then that means that the upward force and the downward force are balanced because there is no acceleration. Since the upward force and downward force are balanced, then that means the normal force, what the scale is going to read, is going to be exactly equal to what his weight is. Now, as he starts to move downward, his motion is downward and he's speeding up. Now, if you remember from the first unit, whenever you have velocity and an object is speeding up, so the velocity is downward and it's speeding up, that means that the acceleration has to be in the same direction. That's what speeding up means. Slowing down means that the velocity and acceleration are in opposite directions. So speeding up, he's moving downward, acceleration has to be downward. Newton's second law says net force equals mass times acceleration. So since the acceleration is downward, the net force also has to be downward. With a downward net force, and the downward force can't change, that means the upward force had to decrease in order for there to be a net force that is downward. So the upward force, which is the scale reading, has to be less than his weight in order for him to accelerate downward. Now we get to a point where we're moving at a constant velocity. As we're moving downward at a constant velocity, that means that there's no acceleration. With no acceleration, there's no net force, which means the upward force and downward force, the scale reading and his weight, have to be equal to each other. So the scale is going to read exactly equal to his weight. Next, we're slowing down. Now we're moving downward, and if you remember, an object that is slowing down, the velocity and acceleration have to be in opposite directions. Since he's moving downward and the velocity is decreasing, he's slowing down, that means acceleration has to be upward. If the acceleration is upward, that means the net force also has to be upward. With an upward net force, that means the upward force, which is the normal force, has to be greater than the downward force, which is gravity. So his normal force, or the scale reading, is going to be greater than his weight in order to stop him. Now we get to the bottom and the doors are about to close. I'm sorry, are about to open. As the doors are opening, we're not accelerating. We're stopped completely. And since we're not accelerating, that means the net force is going to be equal to 0. If the net force is 0, then that means the upward force and the downward force are balanced, and the force of the scale is going to be exactly equal to his weight. So we start at the beginning where the scale is going to be equal to his weight. He starts accelerating downward, so the upward force has to decrease. The scale is going to read less than his weight. As he's moving downward at a constant velocity, that means the upward force is balancing the downward force since he's not accelerating. So it's going to be equal to his weight. As he starts to slow down at the bottom, moving downward, that means his acceleration has to be upward. So the upward force has to increase. And then when he's at the bottom and he's standing there not accelerating, then that means the upward force is going to be exactly equal to his weight. So this is an example that I did on an elevator as I rode on it. You can see here that my weight was about 1250. As I began to move downward, the upward force had to decrease in order for me to accelerate downward. And then the upward force was exactly or about equal to my weight as I moved at a constant velocity. Then when I got to the first floor, the upward force had to increase to stop me. Now this was me at the bottom, the first floor, as I was waiting for the doors to close again to accelerate upward. As I accelerated upward, the upward force had to increase, and then this was me riding to the second level, and then the upward force had to decrease at the top in order for me to slow down. And then again, this was me at the top, and then as I accelerated downward, my upward force had to decrease, and then I was riding at a constant velocity. And then when I got to the first floor, my upward force had to increase to stop me at the bottom. All right, we're going to apply this example now to a man who has a weight of 1,000 newtons and has a normal force applied to him of 900 newtons. What is the net force and acceleration that is acting on him? Well, the net force should be pretty easy. He has an upward force of 900 newtons and a downward force of 1,000 newtons. So to add his forces together, 900 plus a negative 1,000 newtons is going to give us negative 100 newtons. So his net force is downward at 100 newtons. Now what's the net force acting on him? Negative 100 newtons. The acceleration, net force equals mass times acceleration. The problem is I don't have the mass here. I need to figure out his mass. But I do have his weight. Now weight is going to be equal to mass times the acceleration due to gravity. That's what F sub g is. 1,000 newtons is his weight. That's going to be equal to his mass times 9.8. Divide both sides by 9.8 and I get a mass of about 102 kilograms. Now I can plug into Newton's second law where net force equals mass times acceleration. Net force equals mass times acceleration. The net force is negative 100. We found that up here. His mass is 102. Divide both sides by 102 and you get an acceleration of negative 0.98 meters per second squared. On this problem, we have a man who has a weight of 850 newtons and he's on an elevator that's accelerating upward at 2 meters per second squared. So what is the normal force? What is the upward force that's acting on him? Well, we have his weight, which is 850. If you remember from the previous problem, we have to probably figure out his mass. When we're talking about acceleration and Newton's laws, we got to have mass and acceleration, so we need to find his mass first. With his weight being 850, the force of gravity is going to be equal to mass times gravity. That's 850 equals mass times 9.8. Divide both sides by 9.8, and that gives a mass of about 86.7 kilograms. Now his net force, we have an upward force of normal force and a downward force of gravity. That's the net force. That equals mass times acceleration. Well, we have his mass and we have his acceleration, so we'll go ahead and plug that in, and we get that his net force is going to be equal to 173. And we found his force of gravity, we know his force of gravity from the problem. It's 850, so we add that to both sides and we get a total of 1,023. Now hopefully that kind of makes sense, because in order for him to accelerate upward, he has to have an upward force that's larger than his downward force. To accelerate upward, not only does the normal force have to balance that 850, but it also has to push him upward and accelerate him so that he can accelerate upward and have his normal force has to be greater than his downward force of gravity.